GATE 2019 Metallurgical Engineering. Question 8. Consider electrode deposition of copper on a copper electrode from an aqueous solution containing 0.5 into 10 raised to the power minus 3 mole per centimeter cube CuSO4. It is given that the Faraday's constant is 96500 coulomb per gram equivalent. Assume the transport of reactant is rate limiting and mass transfer coefficient is 10 raised to the power minus 4 centimeter per second. The limiting current density in milliampere per centimeter square will be. Now in this problem, it is given that the copper electrode deposition is taking place in an aqueous solution of CuSO4. Now the Cu2 plus ions from the electrolyte are going to move towards the cathode, and at cathode the Cu2 plus ions will gain electron and get deposited as copper atom. Now here you need to pay attention to this term mass transfer coefficient. Now what is mass transfer coefficient? Mass transfer coefficient, it is defined as the ratio of mass transport controlled reaction rate to the concentration driving force. Now what are these two terms? See, the concentration driving force, it is expressed as delta C, and rate of reaction, it is described by limiting current density. Okay, so the limiting current density describes the rate of reaction. That is, what is J? J is diffusive mass flux, or in our case in this problem, since we are dealing in moles, so diffusive molar flux. Now you must understand what is diffusive mass flux. Okay, it is the rate of mass diffusion of chemical species in a stagnant medium in a specified direction. Okay, or in other words, it is the mass transfer by diffusion per unit time, per unit area normal to the direction of mass transfer, and the unit is mole per centimeter square second, and mathematically it is equal to I upon NF. So you can write this equation as the mass transfer coefficient is I upon NF delta C. Okay. Now what is delta C? Delta C is nothing but Cb minus Cs. Okay. Now what is Cb and Cs? Cb is the bulk concentration. Cs is the surface concentration. Understand? Now by the very definition of limiting current density, we understand that the current density is known as limiting current density when maximum reaction rate is permitted by the mass transport phenomenon. So electrode reaction will reach its limiting rate when the concentration of reactant drops to 0 at the surface interface. Okay, so when Cs becomes 0, the current density becomes limiting current density. That is by the very definition of limiting current density. Okay, so this expression is simplified as I upon NF Cb. Okay, because Cs is 0 and this I is replaced by limiting current density. Okay, in this problem we are required to find limiting current density, so I am going to use this relation. I will write it again. IL is NKFCb. Now if we put all the values that are given in the problem in this expression, we must be able to find the value of limiting current density. So what is N? N is number of electrons that are taking part. So since on cathode copper ions are gaining 2 electrons to convert to copper metal, so N will be 2. The value of mass diffusion coefficient is given to be 10 raised to power minus 4 centimeter per second. The value of Faraday's constant is given to be 96500 coulomb per mole, and the value of bulk concentration of copper ions, it is also given to be 0.5 into 10 raised to power minus 3 mole per centimeter cube. So the product comes out to be 9.65 into 10 raised to power minus 3 ampere per centimeter square. You must be wondering where this ampere comes from. See, in the relation, it is coulomb upon second. So by definition of ampere, it is 1 coulomb per second. Okay, so 1 coulomb per second is 1 ampere. So in terms of milliampere, it can be written as 9.65 milliampere per centimeter square. So 9.65 milliampere per centimeter square is the limiting current density for copper deposition. If you want to know more about this concept, kindly refer lecture 14, Environmental Degradation of Materials by Dr. Kalol Mondal, Department of Metallurgy and Material Science, IIT Kanpur. Thank you.